Now we are finally ready to dive deep into organic chemistry. We talked about chemical bonding in the last video, so check it out before you watch this video. In this episode, we will finally talk about electronic effects in a bond like inductive effect and resonance. When two different atoms combine to form a covalent bond, we have seen it as a tug of war between them for the electrons. The stronger atom, which is more electronegative, will pull the electrons more strongly and make the bond polar. This unequal sharing of electrons is called the inductive effect, and we can use it to judge several properties of a compound. Atoms or group of atoms that pull electrons strongly towards them have negative inductive effect, and atoms or group of atoms that push electrons the other way have positive inductive effect. Before continuing further, let's talk about Lewis acids and Lewis bases. A Lewis base is a species that is willing to donate a pair of electrons, and a Lewis acid is a species that wishes to accept a pair of electrons. Roughly speaking, Lewis acids can be called electrophiles and Lewis bases can be called nucleophiles. These two are not the same thing, but for now we can treat them as such. This ties into the inductive effect, as if an atom is connected to a species with a highly negative inductive effect, it will be sucked off its electron and would now wish to gain electrons, hence acting as an electrophile. Electrophiles and nucleophiles form the basis of organic reactions. Now, let's talk about resonance. Resonance is a strange phenomena that many people find difficult to understand. An organic compound can have many different structures because the lone pairs of an atom can drop down into a sigma bond and form coordinate pi bonds. You may think that the compound would repeatedly shift between all these structures, but in reality, it exists as a sum of all these structures called a resonance hybrid. Now, let's look at how these resonating structures are formed. A lone pair or an empty orbital next to a pi bond can undergo resonance by breaking the pi bond apart and forming new pi bonds. The arrows on the screen show the movement of electrons and are very important in understanding resonance. Let's look at some examples like CO3 2-. In this species, a carbon atom is connected to a neutral oxygen atom via a double bond and two negatively charged oxygen atoms with a single bond. These oxygen atoms have an extra lone pair, so they can drop down and form a pi bond, breaking apart the pi bond of the neutral oxygen atom and putting a charge on it. For another example, let's look at aniline. The nitrogen has a lone pair that can drop down and break the pi bonds, so on and so forth. A notable exception could be this compound, a benzene ring where one carbon atom has an empty orbital. This compound does not have resonance with respect to the empty orbital, as that empty orbital is not in the plane of the other pi orbitals in resonance. The stability of a resonating structure can be determined using various factors. A structure that has a complete octet is much more stable than a structure with incomplete octets. As a rule of thumb, carbon atoms with a positive charge are not stable. Just like inductive effect, resonance can have positive and negative effects on a compound. If a species donates electrons, it has a positive effect, and if it takes electrons, it has a negative effect. The effect of resonance on a bond's polarity and stability is much higher than the inductive effect. In the next video, we shall see acidity and basicity of organic compounds using electronic effects, and we'll also learn about hyperconjugation. Until then, make sure to subscribe to the channel and hit the bell icon to get notifications whenever I upload a new episode.